Hi, my today's presentation is about applying LiDAR sensors on the roadside to detect animals approaching or entering roadways. So that can provide a bunch of detailed information and trajectory knowledge of animals and vehicles for safety applications or other analysis. I'm Hao Xu, Associate Professor at Civil and Environmental Engineering, University of Nevada, Reno. So LiDAR sensor is simply shoot out laser beams based on the flying time of laser beam to measure and detect the surrounding objects at high accuracy, at a centimeter level accuracy. So right now, the majority of LiDAR sensor applications are still on the vehicle side for autonomous vehicle or semi-autonomous vehicle. And the LiDAR sensors can, in fact, when they provide a lot of detailed spatial and accurate spatial information, in fact, that can be very useful when we move the sensors from vehicles to the roadside. This is exactly what we have been doing in the past few years at the University of Nevada, Reno. We installed the LiDAR sensors at urban intersections, rural roadside, along freeway segments for collecting high resolution movement information and behavior information, and then for different applications. So LiDAR sensors, especially current LiDAR sensors we use for sensing and use for autonomous vehicles. Generally, we can separate them into two different types. The first one is a 360-degree LiDAR sensor. We also call it a rotating LiDAR. So this type of LiDAR sensor is shown like the first picture here is a Velodyne 32 channel. So this sensor shoot out the 32 laser beams, and all the 32 laser beams, they were aligned along the vertical line. And every second, all the laser beams rotating like a 360-degree 10 times. That means generate 10 frames data every second. And non-rotating LiDAR is especially good for vehicles, because for most of the vehicle manufacturers, they don't want to see the 360-degree LiDAR sensor on top of that vehicle because it does not look cool for the vehicle owners or drivers. So this is why the recent LiDAR products, there are many, they were only for one direction, but they can be easily integrated with the vehicle body. So like this type of LiDAR sensor is not a 360-degree, it's only one direction, can be from 40 degree to 100 degree. And for one vehicle, the surrounding detection, we may need several LiDAR sensors. So similar for intersection, when we use one 360-degree LiDAR sensor, we may just put one LiDAR sensor or two LiDAR sensors at one intersection or one segment. But for non-rotating LiDAR, we may need to have several ones. Okay, so for rural wildlife detection, normally the sensing system, we need to have three major components. One is the sensors. So it can be LiDAR sensor, cameras, radar, thermal, or all different sensors. Okay, the second major component is the power supply. Especially in the rural area, we barely be able to get long-term permanent power supply. So this is why for our roadside and animal detection and sensing testing bed, we use one ITS trailer and installed a wind power turbine, we installed solar panels, we have batteries, and also we installed a backup generator. So anytime we make sure the power supply is there, 24 hours, 7 days for all the seasons. Okay, the third component for a roadside animal sensing system is the edge computation, so our processing unit. So for different sensors, we may have a different processing units or roadside computers. So all these processing units can be housed in these ITS cabinets. Okay, this cabinet can also house the remote communication devices like LTE router, Wi-Fi connection, and power converters. Okay, so for the LiDAR data, raw LiDAR data is just looks like this. It's all points, high density points. So these points, they are not like pictures or videos, they are vivid. So and very friendly to human eyes. So the points from LiDAR sensor, they are the reflection of laser beams from all the different surface. And based on that, it generate these kind of high density points. It's like a cloud. This is also, we call it cloud points for LiDAR sensor data. Although it's not human eye friendly, but it's very computer friendly. It is quite easy for computer program to process. So here just examples. When we, for the 3D data cloud points, when we look at from top to bottom, so here's how it looks like a truck, a vehicle, and 3 houses. And these lines, they are ground reflection, road surface reflection, and also we can see points reflected by roadside vegetation. And if we tilt the data, 3D data, to the side of the traffic, we can see this is the shape and look of trucks, vehicles, and the same 3 houses, and roadside vegetation and road surface. So the third picture is another example from relatively low resolution LiDAR sensor, but we can still see the deers, a herd of deers crossing this overpass facility. Okay, so for LiDAR data processing, yes, so here there are too many points, and in fact, 95% of these points, they are not useful. They are just vegetation, roadside or road surface. We are not quite interested in those data. We are only interested in road users, including animals. So in our data processing, first we remove all the background points, and then we have only trucks, vehicles, and horse points here. And then we use machine learning algorithms to group those points based on their special distance. And also using AI method to classify each object to its specific classification, like whether it's truck, vehicle, horse, or animal, or pedestrian, bicycle. So in fact, one major research achievement of our program is significantly improved the accuracy of classification. That means when we detect an object in the LiDAR data, in the real-time LiDAR data, so right now we have a very high accuracy to know what type this object is. So like right now, especially when we use the ADA boost and RUS boost, these are all classification algorithms in deep learning in AI. So it's really the bottom 2 methods. They provide 99% accuracy for all the urban road users, vehicles, pedestrians, cyclists, and wheelchairs. We apply the same methodology for rural area for White House crossing. It provides the same level accuracy to separate vehicles and horses and other big animals. Okay, when we have those objects and the classification of each object, frame by frame, we can track the movement of each object. This is how we can generate trajectories. So by nature, the LiDAR data only have X, Y, Z coordinate based on LiDAR as the center point. In our data processing, we geo-reference all the trajectory data into GIS, global coordinate system. So we can easily map all the trajectory and the movement information onto a map in GIS. And here the example showed red dots, they are trajectories of horses crossing the highway and walking along the roadside. And all the green dots, they were vehicle trajectories. Okay, when we have the high accuracy, high resolution trajectory information of all those objects, animals, vehicles, pedestrians, so we can use this accurate, detailed, special information to do many different things, different applications. Definitely, it can be used for roadside signal control. It can be broadcasted through connected vehicle communication So drivers or autonomous vehicles can receive all the alerts and information even without a roadside signs or units. And also, even for the base application, when we have all the GIS layers and the map, we can easily do the offline GIS analysis and the safety evaluation to see where and how often animals crossing the road and how they influence the traffic flow and how drivers and animals interact with each other. So here, just a very simple example to show offline GIS analysis and the safety evaluation. So first, although we deploy the LiDAR sensor and the trailer at the roadside intersection, rural roadside, is for animal detection. But the system provides 24-hour, 7 days, all traffic information, including volume, speeds, acceleration, deceleration, and even headways between all the vehicles. So that can be additional information asset for agencies. And when we can know all the vehicles' movement anytime, if there is a horse or deer or animal crossing this highway, rural highway, we can immediately, the system immediately know that and also can record the before-after vehicles' behavior. So here, just in 1 week, here's one example. 1 week, we identify about 12 events of horse crossing. So every event, it may with like one horse or may several horses, a herd of horses. And with the trajectory information of horse and related vehicles, we identify the waiting zone. To identify this zone means the horses were approaching the roadway. And this is a crossing zone. That means when horses were in this zone, they were actually crossing the road. So based on all the specific, special, and time information, in fact, we can tell and report every vehicles, whether they yield or no yield, and when and what's their related speed for the yield or no yield events. Every blue dot here means one vehicle. So when the vehicles dot located in the first 2 columns here, that means the vehicle didn't yield to the horse crossing, and their speed was quite high, 40 to 50 miles per hour. And this center column, when points fall into this group, tells us these vehicles yield to the horse crossing, and their speeds were relatively low. So because it's every speed in the detection zone, so the 2 vehicles here, they may stop, and several vehicles here, they may just slow down. And these points will not really yield or no yield. The vehicles coming after the animals are already crossing the road, so they will not really yield for the analysis. So this is just one example of offline analysis. So right now we are working with our collaborators to test and integrate different roadside animal sensors like radar, thermal, camera, and LiDAR to identify their performance and to see how much improvement we can achieve when we integrate or merge the different sensors. So we will also test the roadside warning signal and the connected vehicle connection. Okay, that's it for my today's presentation. Thank you, everyone.